All right, guys. So I'm making a short video just to cover some subjects that I see you've encountered, which may be difficult to understand, starting with these projective measurements. So we understand quantum systems to be a sort of vector in Hilbert space. This allows us to express them like a linear combination as done so, where we have some amplitude multiplied by the vector in that direction. And the idea here is that these individual vectors are perpendicular to each other. So any inner product between any of these three or however many would yield zero because they're perpendicular. Now, that means that if we imagine this, not that it actually is in Euclidean space, but if we imagine that our quantum state somehow has some direction and length in Euclidean space, then it can sort of be decomposed and projected into, you know, being expressed in terms of its basis vectors, which is sort of what we see right here. Now, we know from classical linear algebra that if we can decompose a vector into its basis vectors, we sort of do this by doing these like projections, and that's basically what a projective measurement is. It is a measurement which sort of um, measures how much the quantum state sort of points in that direction based on the specific basis vector you're trying to measure in terms of. So here's an example. If we have pi, where I is like, any direction. So it could be like 0, 1, 2, out of however many dimensions we have. Then it is expressed as the outer product of just that ket. So, or just that ket. So it will be the basis vector multiplied by its dual correspondence. Um, And this basically projects the state when you apply it onto the state you're measuring into this state. It is sort of like asking if we measure this specific substate or this specific ket out of our quantum system, how much does it point in that direction? Let's see. There's a lot to cover, so I sort of wrote it out already. So if our ket here is normalized such that it has this property that its inner product is 1. Basically that the basis states or basis kets have length 1. Then it also has the property that when you square it, it's the same length, which makes sense for something that, or like it's the same matrix, which makes sense for something which has length 1, and also has the property that it's Hermitian, which if you haven't yet heard it in quantum physics, Hermitian, this operator daggered, means it's been complex conjugated and transposed. Now, I mentioned earlier that these are supposed to be perpendicular to each other or orthonormal, so also with length 1, the basis making up this quantum state. Um, this operator then has the property of projecting the span subspace by the basis vectors into that state. Basically what that means is that if we have some quantum state, which, we've seen right here, like let's just say that this state is this one I've written out over here, and I then measure it with the projector of, say, let's just say it's psi 1, psi 1. Notice how this right here is the projector, so it's in this form over here, but just for the specific basis ket psi 1 corresponding to this one. Um, this then has the effect of sort of multiplying, if we imagine it's right here, it multiplies onto this term, this term, this term. Now, because we just established that the basis kets are perpendicular to each other, orthonormal, the product of this specific case with this vector is going to be 0 because psi1 and psi0 are normal to each other. It's also going to be 0 for this basis vector because psi1 and psi2 are perpendicular to each other, and for any other vector except this one right here, c1 multiplied by psi1. What will happen is that we like specifically pick out the state um, psi1, and we get this inner product. Well, there's not a lot of space. It says psi1 right here. So we get this inner product from applying our projector of psi1 onto the full quantum state, and it projects into that basis vector. Psi1 multiplied by psi1, this inner product, that just becomes 0, or sorry, 1. So as a result, all of this becomes C1 multiplied by psi1, because there's still this remaining psi right here. And this basically tells us, it's almost like asking our quantum state psi, how much does it point in the direction of psi1? We ask that question by applying the projector for psi1, and the answer is that it points in psi1 by some amount corresponding to the amplitude of psi1, c1. Okay, cool. Now I have an example here, actually, that I wrote out. I completely forgot that, actually. And it says that if our quantum state is psi, corresponding to a linear combination of equal amplitudes for each term of ket1, ket0, ket1, and ket2, and we apply, say, the projector for ket1 or state 1, but it could be anything in principle. It could be 0 or 1 or 2. If we apply it, then we here have a very concrete calculation. So here's our projector. Let me contrast it better. Here's our projector, and it gets multiplied onto this parentheses, which is the linear combination. So we just multiply it in here, etc. What we get is the product of the projector with each state. Now we see right here that we get an inner product for this term of bra1 times ket0. These are normal to each other, so the product of this is 0. We also get the projector multiplied by ket1. Now here we have an inner product of the same, what's called like a basis vectors, and we know it's normalized to 1, so it gives us a value of 1. And here we once again have the same scenario as previously as over here, where we have an inner product of two perpendicular or orthonormal vectors, basis vectors, and so this becomes 0. Um, let's now look at the specific case, which is what happens here. Since this becomes 1, it sort of just becomes the number 1 multiplied by this ket here, which is like the leftover right here after this one has been expanded in an inner product. So we get the resulting state right here, which is 1, 1 over square root of 3 multiplied by said projected basis vector. And it tells us basically, that it's like how much does the quantum state psi point in the direction of ket1? Well, it points in the direction of ket1 by magnitude um, or amplitude 1 over square root of 3. Next up, let's look at subsystem measurements. So what we've described so far is just like a collection of, or like not a collection, but like single systems. But we can actually have multiple systems and describe them as one whole quantum state. And we can do that by combining Hilbert spaces. So say that we have two systems that we want to describe in one quantum state. Now, each system correspondingly is described by their own Hilbert space. It's very convenient to think of qubits because that's sort of your focus. So let's just think of it as this being the Hilbert space in which qubit 1 exists or is described by, and this being the Hilbert space that qubit 2 is described by, corresponding to, let's just say that one is owned by Alice and the other is owned by Bob. Then this composite Hilbert space describes one total quantum system, which is a combination of both of their qubits. Now, if we actually have this system describing one whole quantum system, but we only want to describe a measurement being performed on one of these two subsystems, we can actually combine operators in much the same way that we can combine the Hilbert spaces. Notice that their combination is permeated by a tensor product. This x right here, which is circled. Likewise, we actually do that for our products. So if we define some measurement operator, which we call mi, for like it is indexed to like measure the ith. Okay, so like kind of like up here, how p1 measured the 1th ket. I sort of just arbitrarily measures the ith ket, but specifically for Alice's subsystem. Notice here how this is the projector corresponding to Alice's system, measuring the ith ket of her subsystem, and it's been tensor product with a I'm blanking, what's this called? Identity operator for Bob's subsystem. So how do we interpret this object? Well, it's basically a measurement which measures, or like does a projective measurement on Alice's subsystem while ignoring Bob's subsystem, because the identity operator or the identity matrix applied on a matrix just returns said matrix. Cool. So now we have a composite quantum system in which we describe necessarily only just one measurement. If you wanted to do Bob's measurement, you could obviously just do Bob's. If you have like hundreds of qubits, it would just be like one long row of identities multiplied or tensored by each other, with one exception somewhere where you wanted to measure a specific subsystem. Now I have an example demonstrating how it is that we use it. So if we imagine that we have a quantum system corresponding to this ket here, this ket psi, and it is a combination of Alice and Bob's qubit, where it is a superposition of both being 0, one being 0 and the other 1, one being 1 and the other 0, and both being in the state 1. For this system, we want to perform a projective measurement of the first ket, or like the ket 1 in Alice's system, meaning we want to sort of do a projective measurement in Alice's system onto the basis vector ket1, which necessitates that we ignore Bob's system, which is why we just use an identity right here. Let's see what happens. So if we apply our measurement onto uh, our quantum system, we start out by simply just multiplying our, but I should also just mention this combined counts as one operator for the full system, even though it is composed of two individual operators for their own respective system. So we can actually treat this as a one entity and just like move it around as if it's one thing. So we sort of like take this full thing, multiply it in front of this, multiply it in front of this, in front of this, etc. And we get this long expression right here, which is the full measurements operator applied to every ket in this quantum system described by a by 2 qubits. I should mention regarding this notation, the fact that there's two sort of values inside it, it just means that it's like shorthand for Alice's qubit vector product or tensor product with Bob's qubit. It's sort of just shorthand to refer to both of them, so I don't write out all of this mess. Um, Now this is quite a lot to calculate. I didn't bother calculating it all, so I'm just gonna do like two important examples out of these four. The first one being this one. So notice that we have um, two operators tensored together, multiplied onto two kets tensored together. Again, according to this. Now this follows a specific identity or property related to tensor products, which is this right here. So if you have a tensor product multiplied by a tensor product, it corresponds to A multiplied by C tensored with B multiplied by D, which is why you get this here. A very easy way to think of it is just that each thing has its own place. So if you have like 10 different tensor products together, so like the first like element goes together with the first element, the second element goes together with the second element. So if you had like a third uh, tensor product here, it would just be like A times C times E, etc., etc. So let's see how that plays out. We multiply our projector onto the first ket, which is ket 0, and our identity onto the second ket, which is also ket 0, where this is Alice's and this is Bob's. And we get this expression down here, where we once again have the first, or the projector for ket 1 onto Alice's state, tensored with the identity onto Bob's state, and this tensor is, like I said, just from this identity over here. And we see that a projective measurement onto a ket 0 that is normal to each other. To write it out again, that would be like performing this projective measurement onto ket 0, and we see that this right here is an inner product of bra 1 with ket 0, which is 0. So this entire expression right here becomes 0. Um, the same can be said for this situation right here, because here the projector onto the first ket is also just 0, so this entire expression would also be 0. Now if you look at this third term over here and sort of use the identity to the right to rewrite it like this, we have the projector onto Alice's qubit in the state 1, tensored with the identity onto Bob's qubit in state 0. Well, Bob's whole aspect isn't really that relevant because it's just the identity. So what happens here? Well, um, ket 1 is parallel to ket 1, so it just gives us this expression right here. And if we sort of recombine it into this notation in accordance with this expression up here, it just goes back to being this state. And we can do that as a sort of for the last time, just with this expression right here. P1 onto ket1, identity onto ket1, um, no orthonormal basis vectors, so this also becomes a concrete non-zero product, and we get this expression down here. So what does this tell us, actually? This tells us that if Alice does a projective measurement, so performs a measurement which makes her quantum system or her qubit into, or its wave function collapses into the state 1, then the remaining quantum system will become this system. So uh, because the first qubit is Alice's and she measured it to be 1, the other qubit corresponding to Bob's qubit is either 0 or 1. Now I'll actually come back to this because this is actually a really important story, but I can't tell why just yet. But it has to do with communication. Next up, let's talk about another really important aspect called a tool called the density matrix. So the density matrix is basically just like I said, it's a tool that contains all the information about a quantum system. So it's a more universal description of a quantum system, more universal than a wave function, because a wave function can only describe quantum systems, also linear superpositions, while a density matrix can describe uh, other systems as well, which aren't necessarily superpositions. And we'll see why in just a second. So the density matrix is given by the outer product of the quantum state you're dealing with. So if we take an example, such as the computational plus state, which is just a equal linear sum of computate or of a linear combination of ket0 and ket1. If we then take this outer product, we get, every combination. I think I showed this earlier today. We get 0 multiplied by 0, 0 multiplied by 1 multiplied by 0, and 1 multiplied by 1. Now, notice that this almost sort of corresponds to a sort of coordinate set. Um, well, we can actually extend that idea to matrices. So if we take this sum of outer products with the basis vectors, we can actually draw a correspondence to matrix coordinates. So 0, 0 is like the 0, 0 coordinate in a matrix. 0, 1 would be, I'll admit, I forgot what's first and second axis in a matrix. I think this is 0, 1, either that or it's this one. I forgot, but you know what I mean. So we notice how there's this factor, 1/2. I sort of just like pulled it outside here to make it convenient to write out the ones. But basically, we have like a value of 1 here. So like a 1 multiplied by this element, 1 multiplied by this element. That's where all these ones comes from. And just because they're all divided by 2, I decided to draw that factor out. But okay, let's analyze the anatomy of this matrix. There are two important things to notice. First of all, we have diagonal elements. These diagonal elements correspond to the probability of measuring that state. So because this element corresponds to the outer product of ket0, it basically corresponds then to the probability of measuring ket0. That is, if we had our state and it was a linear combination and had an amplitude, uh, psi0, basis vector, psi 0, etc., etc. The probability of measuring this state would be this value squared, or like absolute squared, and that concrete value is this number. This one right here would then correspond to this one, obviously, and if we had a higher level systems, there would obviously be more diagonals. It could, in principle, be infinite. Now, but there's another aspect to this matrix, which is the off-diagonal elements. The off-diagonal elements are something we call quantum coherences. A coherence is sort of like a measure of how quantum is our system. Now, that doesn't really make a lot of sense, and it's hard to explain without drawing contrast to the other example. But basically, this is what we call a pure state. And basically, if there's anything in the off diagonals, it tells you that the system is in fact in a sort of quantum superposition. This is in contrast to something called a statistical mixture. So if you instead have a system described by the density matrix that looks like this. Notice that we do have values here that describe the probability of measuring either state 1 or state 0, which is true, like a system doesn't have to be quantum to be random. Flipping a coin is also like performing a 50-50. So measuring a quantum system doesn't necessarily have to be like really fancy. It could also be just a statistical 50-50. And the way we can tell it apart is that this actually doesn't have quantum coherences. The reason why this is not like a pure quantum state is because and this is like probably a proof we'll be doing next week, would be my guess, but it is impossible to write this density matrix as a outer product of a quantum state. Because if you could, that would mean that it's in a superposition. But yeah, you can't write this as like a multiplication of a linear combination. Or what's it called? You can't decompose. There's a word I'm looking for, but I forgot. Um, we can actually like put this into perspective with the Blosphere. So as a reminder of what the Blosphere is, it's a incredibly powerful visual tool to describe every possible uh, state that a two-level system can be in, a qubit. So up here at the North Pole, we have ket 0. At the South Pole, we have ket 1. And then at the equator, the entire equator corresponds to the quantum system being in a superposition, equal superposition of ket 1 and ket 2. I have to be very careful not to say 50-50 probability because there is actually a semantic difference that we have to be very careful, and it's related to these two objects. So if we look at this statistical mixture, the way that we can interpret this is by saying, okay, the system is 50-50. It's 50%, or like statistically, it's 50%. 50% of the time you're going to be measuring 0, and 50% of the time you're going to be measuring 1. But it's not a superposition. So that can sort of be interpreted as saying that you have like a vector, which is halfway pointing towards state 0 and halfway pointing towards state 1. Now, two vectors pointing in opposite directions, but with the same magnitude, which is a half, like their magnitude, they're going to cancel each other out. So when you take the sum, it's just going to be 0, and it's sort of just going to collapse into a dot on the center, in the center of the sphere. Now, a dot obviously has a length of 0. In other words, there isn't really like a vector corresponding to some radius pointed outwards. This is a property of a system being a statistical mixture. It could also be a vector, like there could be a vector pointing in some direction. However, the system is in a pure quantum state only if it has length 1, meaning pure quantum states, superpositions, exist exclusively on the surface. All other states corresponding to statistical mixtures exist inside it. Now let's contrast this with this state we have had up here. This was the plus state. And notice how this is a sum of vectors, but not in the statistical sense, but in the sense that we had this like coherence corresponding to it. And that's because it now has phase. Uh, it is located right here on the plus sphere. And if we added phase to the quantum system, which would usually be some factor here, so it could be I, but in principle it could just be some continuous phase, e to the I phi, or phi, no, e to the I theta. So our superposition, which is different from our statistical mixture, has a radius of 1, and the every possible quantum pure state which has equal probability exists on the equator, and the only difference between the infinite like or the infinite possibilities is just that it has like a continuous phase. Fuck, I lost train of thought. I thought I was gonna say something. Yeah, I hope this makes sense. You know, it, basically just this like aspect about the vector describing whether or not it's a quantum state or statistical mixture based on its length. If you have any like, if anything's confusing, please do like send me a message, and I'll make sure to like cover what's misunderstood or what's hard to understand. As a last subject, I want to cover partial trace and the reduced density matrix. So, like we saw earlier, if we have a joint system that we can describe in terms of a like not this so far, but if we have like a joint system such as this, where we have a system for Alice and a system for Bob, if you want to describe the full quantum system they share, it can be described as this tensor product. Now we can actually also use this tensor product to create a density matrix for Alice and Bob's shared quantum system by once again just doing this outer product between their tensor product states. However, if we have a system like this and we say only care about Alice's specific quantum system from this entire description, there is a way we can describe that, and that is by doing something called a partial trace. So we get from this system the density matrix describing only Alice's part of the quantum system by tracing over Bob's quantum system. So that's basically saying uh, every possible combination that uh, sort of Bob's quantum system can contribute to the like full system. If we just sum all of those from Bob's perspective, the only remaining aspect of the quantum system is going to be whatever possibilities are left for Alice. And we're going to see an example in a second. But the remaining density matrix is sort of the object that now contains all the measurement information of the joint quantum system, but specifically for Alice's measurements, or like whatever measurements happens on Alice's subsystem. Um, and the way this works, this partial trace, is just that you sort of sum over the opposite, or like opposite person, because now it's Alice and Bob's, but like you sum over the quantum system of the quantum system that you're not interested in. So, as an example, because we're interested in getting Alice's system from this joint system, we know that the density matrix and their tensor product is defined in this joint Hilbert space. So we sort of just do the same thing, which is that we sum over the entire Hilbert space corresponding to Bob's. And to do this, you sort of have to choose what basis you want to do it in. But like for our case, like it's pretty simple. We just do it in the computational basis. So we sum over all of Bob's computational kets and bras, like as you can see right here. So this is sort of like what we do for the partial trace. And it leaves us with Alice's subsystem. Uh, Now this may all be like a little confusing, so like I've also made an example for this just to demonstrate that like it's not as bad as it sounds. So if we hypothetically start out with a quantum system, that being the Bell state corresponding to the entangled state of both qubits either being 0 or both qubits either being 1, then we see that the density matrix for the joint system can be described by this linear combination of outer products, and it seems familiar to the one we saw earlier. Now, if we trace over Bob's system in the computational basis, corresponding specifically to just his computational 0 and computational 1, then it sort of just means that like we sum, like we take this parentheses and we sum over every combination of like 0 here, 0 here, multiplied onto each one of these, uh, plus, 0 here, whoops, like 1 here, 1 here, etc. And what it leaves us with is this sum down here. Um, Now, the funny thing about this is that didn't we just say that a quantum system, which is expressed like this, like let's try to draw out this system in terms of a density matrix. It looks like this. Now, didn't we just say that this object right here is a statistical mixture for describing the system? Because we have our probabilities of measuring the object right here, and we have our quantum coherences right here, or should I rather say our lack of quantum coherences. So when viewing this, one would naturally assume, well, obviously, it appears to be a statistical mixture because there's no quantum coherences, so it's not a quantum system. And that is true locally. The thing is, because we're actually looking at an initially entangled state, we can actually view this from like two different perspectives. We can look at it locally. Basically, if Alice had this qubit and she measured it, she doesn't even in fact have to know that it's entangled. Because to her, if she just like had a bunch of qubits which were entangled with qubits in Bob's lab, and she didn't know they were entangled, and she just started measuring them, they would obviously just look like random 50-50s. So from her perspective, it would just look like it's in a sort of mixed state, like there isn't really any correlation for the statistics of the measurements. However, if Bob knows her measurements and then performs measurements on his own qubits, he would see that there's a one-to-one correspondence in statistical measurements. So hypothetically, if Alice had 5 qubits and they were entangled with 5 qubits in Bob's lab, but she didn't know that they were entangled. And she then performs a measurement on each of her qubits. And let's say the values are 10100. These are just like random values to Alice. It looks like more or less just like a 50-50, which is just like a statistical mixture because she is in fact just doing like a random 50-50. Her statistics are returning her like a 50% probability. Now, she would have no reason to suspect that these were entangled with Bob's qubits. However, if Bob could sort of know what qubits she measured, and he then measured his own, he would see that he would get the exact same values for his qubits because there is a correlation between them. Now, oops, as one would expect, because you can see it right here. So if Alice measures 0 and Bob then measures the same like his qubit, it would also be 0. Or if she measured 1, it would be 1. So why is it that this looks like a mixed state? Well, that is, like I said, because to her, she still has local, like random statistics. Now, but while like globally, they are correlated, but locally, she has no reason to suspect that they're entangled. Now, this actually tells a bigger story than we can see immediately, and it sort of relates to what I mentioned up here about this, like, I think it was partial trace. Because notice that this tells us that if Bob didn't if Bob didn't know, or if he doesn't know what she's measured, he just knows that she's measured her qubits, and then he can measure it himself then. Um, it would appear to be locally a statistical mixture, which means that even if you entangle qubits and perform measurements on one, you can't affect the other besides just being able to predict what the outcome will be. As a consequence, it means that you can actually not use entanglement to, say, communicate. This was sort of like something that scared Einstein for a second, but it's been solved in recent times due to this like aspect of understanding randomness. Um, Basically, the story I'm trying to say, or the story I'm trying to tell, is that we can not use entanglement to communicate faster than the speed of light, or should I rather say, like the language that physicists would use is that we cannot communicate non-locally. So if we had like a set of qubits here, and they were entangled with a set of qubits on Andromeda, we wouldn't be able to instantaneously communicate with someone on like in the galaxy Andromeda just by performing measurements here, because at the end of the day, the act of measuring your qubits, like the outcome is random, and the only like difference from it being like, how do I parse this? Your measurements will be random. However, once you've measured it, you are guaranteed to know what the other entangled qubit is going to be. However, the fact that you cannot choose what your outcome will be is sort of what dictates the fact that we cannot communicate faster than the speed of light. Um, so like if like for the same scenario, if I had a qubit here and was entangled with a qubit that was in some lab in the galaxy Andromeda, and yeah, let's just say it was like this system. I can't choose which one I measure, or like I can't choose like what the outcome is going to be of the measurement I perform, but I can't just measure it. So let's say I measure 0. Okay, cool. But from the perspective of whoever is in the lab on Andromeda, if they then measure their qubit and it turns out 0, they cannot distinguish that from them being the first to measure it and just getting a 50-50, or if their result is because you decided to measure first and collapse the wave function. So if neither party plans when they measure the qubit, you can't distinguish whether or not your partner has measured or not. I hope this makes sense and sort of like goes to show that randomness and entanglement, they're sort of almost mutually exclusive, but still not. You know, a measurement of one, a measurement of one qubit will dictate the outcome of the other, but you cannot distinguish it as the second person to measure. Um, I hope this video was informative. I do realize I did ramble a lot. It's been a long day, but I think I got a lot of the subjects more or less covered efficiently. So yeah, I hope you enjoyed. And if you have any other like confusions, please do like send me a message or a few. Like I'll gladly answer. But yeah, take care.